Hi, my name is Dr. Megan Cox. I'm an application scientist at Microcosm, and today I'm going to run through a NIST traceable size standard on the BeNano 180 Zeta Pro. So first of all, I'm going to prepare the sample ready for analysis. So what I'm doing here is just pipetting a milliliter of pre-prepared polystyrene latex. Its certifiable diameter is 100 nanometers with a PSC value of between 96 and 106 nanometers. So this is the system interface. We've got the door, which is just a push top. Got a nice handy little indicator to show whether or not your sample is within the right volumetric range, which it is in this case. So we just pop it in, close the lid, and then we go into the Better Sizes dedicated software. The first interface that you'll come to is the projects interface. This is where you can create separate projects for each sample type that you run, or if you've got multiple students with multiple different projects as well. So currently we've got a Meritics dedicated project, which I'm going to go into the records for. You can see all the previous size measurements that we've achieved. You can toggle between size measurement, zeta potential measurements, molecular weight, and then there are size versus temperature trends and pH. What's nice with the system as well is you can perform a microrheology measurement, which means that if you don't know the viscosity of your carrier fluid for your particle, you can spike it with a known size standard and it will calculate the viscosity for you. So what I'm going to do is run a simple size measurement. So either we can do this in a manual method or by opening an SOP. I'm going to perform an example of opening an SOP. Again, you could have an individual SOP per sample that you look at, but here we've just got a default SOP. So if I go to open, you can see that because I've run 100 nanometer PSL previously, it's auto-populated with the sample name, my initials as the operator, the sample source, which is Thermo Fisher. We're Microcosm, so we're the testing body. And then any additional notes that you want to put about your sample, you can input in the notes section. So going through the different parameters, I'm running a polystyrene latex, so I've got the right optical model loaded. However, if you were running any other samples, you can either select from the drop-down list, or you can add your own material parameters. So if I just reassign the PS latex. So if we're going to now move on to dispersant, we're just using water, but again, if you had any other dispersants, you can click on the More tab and you can see there's a reasonably extensive list here, but again, you can add your own dispersant with the name, dispersant refractive index, viscosity, and then for zeta potential and molecular weight measurements, there's the dielectric constant and the Rayleigh ratio. So press OK to that. The next parameters down are the measurement parameters. The first one is temperature. You can set a pre-equilibration time. The sample's been sat in the instrument for about a minute or so now, so I'm going to leave the equilibration time as 0, but you want to ensure your particles are in Brownian motion, so the random collision of molecules for this technique to be most accurate for sizing your particles. That's the same with all DLS instruments. The standard default equilibration time is around 120 seconds. So if you were to prepare your sample, put it in the instrument straight away, then you'd want that equilibration time to be set. We're running it at 25 degrees, which is default temperature, but you could change that to suit your experiment needs. The next is sample cell. Different types of cells that we can have for this instrument. On the drop-down list, we've got PS cuvette, so a polystyrene standard 1 centimetre by 1 centimetre cuvette. We also have a micro volume cuvette, which can analyse around 45 microlitres of sample. So if you've got a more precious sample. There's then the glass cuvette for if you're working with solvents that might damage the PS cuvette. You've then got the glass micro volume cuvette, similar to the PS cuvette. And then you've got a specific capillary sizing cell as well. And that will enable you to analyse as little as 10 microlitres of your sample, and it draws the sample up as would suggest by capillary action. So I'm just going to select PS cuvette because that's what we've loaded. The next tab is the duration and number of measurements. By default, you've got 3 measurements with a 5-second delay between the measurements. We've got the duration as auto-detected, and we've got also the attenuation as auto-detected. So the attenuation will set the intensity of the laser power proportional to the concentration of sample. So if you have a low concentration of sample, it will attenuate high to allow for the laser to have more scattered light and give the most accurate result possible. There is also, on the correlator function, there is a short time, medium time and long time. So if you're looking at smaller particles, then you could get away with a short-term correlation function. If you've got a polydisperse or a larger particle, you might want to go with a longer-term correlation function. I'm just going to stick with the default, which is the medium time, and then go to the scattering angle. So this system is equipped with 3 scattering angles. The 90° is traditional DLS. It's good for about 90% of the different samples that you will come across. The 173 is almost complete backscatter, and this will have a larger imaging volume, and therefore you'll be able to have a higher resolution of particle sizing. And then the 12.2° angle is predominantly used for electrophoretic light scattering, so for Zeta potential. However, for extremely large particles, you can also use this scattering angle. So I'm going to keep it on 173, and what the detection angle at 173 also enables you to do is you can have either a manual measurement position or an automatic measurement position, and what that means is that if you select automatic, the system will choose the best position within the cell, so whether or not it's close to the wall of the cell or further into the sample cell for measurement. So this is important when you have varying concentrations of sample. It enables you to have a higher concentrated sample of up to 40% weight over volume. And then the last thing is the analysis model that you apply. So general, again, is the default analysis model, but there is also Contin and NLS, which offers a higher resolution for more monodispersed samples. So general is great for a sample that you don't know what might be in it in terms of particle size, and also for polydispersed samples. There are also more advanced settings, so you can apply different fits depending on your sample, and there is also filtration rate. So by default, the BeNano will take the top 80% of autocorrelation functions and use that in your result. But you can set this to 1 and look at everything that the system collects. So this is where you can hone in on really getting the best data possible for your sample. So I'm going to go OK to that. Here, this is where you could save the SOP as a new name, but I'm going to just keep it as the default SOP, and then I'm going to go to Start. In this tab, this is your main analysis tab. You have the intensity fluctuation over time. So this is your scattering intensity. You then have your correlation function that will come up, the intensity size distribution, and then you'll have your independent measurements, so the 3 measurements that we set in the SOP. So I'm going to go to start. You can hear that the instrument starts making some noises. That's what you want to hear. You'll also notice that the green light on the instrument will start to pulse. That also shows that it's starting to do things associated with the measurement. The software also has this really useful little tab at the bottom of the analysis window, which tells you what it's doing. So it's going through the different attenuators to get the right level of intensity of light scattered for the most accurate results. It will then conduct pre-tests, so you'll see that the intensity distribution will come up and you'll see an autocorrelation function. And it will go through these pre-tests until the system deems that it's got the best data. So you'll want an autocorrelation function as close to 1 as you can, with a nice smooth curve, and then minimal sort of variation on the tail edge of the curve. So now it's happy with the attenuation, and it's now moving the position, so the system recognises the measurement position within the cell. So dependent on concentration is where that measurement position will be. And then when it's happy and it's found all its appropriate measurement positions, it will start collecting the data. And you can see after each sub-run of the repeats, it will update the data in a near real time. On the right-hand side, you can see the results. So this again will update in near real time. So you've got Z average of 109.13 nanometers, and then you can see the polydispersity index, and having a low polydispersity index indicates the monodispersity of the sample. So you want that to be as close to 0 to have high purity in a monodispersed sample. So you can see that the first data set has been collected, and it's been plotted on this Z average trend graph. And what we can do at this point is we can go to the main screen, and this is the first data set that has been collected. So for each data set, you can look at the raw data, the intensity distribution, and you can see that we've got a nice autocorrelation function. We've got a size intensity histogram, and you can see the size of each peak. If there are multiple peaks present, obviously the table would be populated. So you can also see the collection information that we've inputted as part of the SOP down the left-hand side. And then if we go to any of the other distributions, you can see that the result subtly changes. This is because the volume, number and area distributions are post data collection algorithms that use so further calculations. And that takes into account this dispersion refractive index and the absorption of your material, so of the PS latex. So you can see that the sizing has decreased. And then if we go across to number distribution, this is where if you had a polydispersed sample and you had more small particles than you do large, it would weight the smaller particles, so you'd see more of them versus the larger particle. Whereas in a volume distribution, if you had lots of smaller particles, then they may only look the same as one bigger particle. So that's because many small particles can fit in the same volume as one big particle. And then you have area distribution, and then you can also look at both the cumulants analysis and the distribution fit to check the autocorrelation function. So as you can hear now, when the system's finished analysing your sample, it'll beep, So if you're off doing other things in the lab, it's a clear indicator that you can load your next sample. So if we go back to records now, you can see that we've got the other two size distributions populated. I'm going to Control Shift and select all three, and then you have this further tab called Statistics and Overlay. So you can see that we've got a beautiful alignment between the three separate measurements that we've performed for this sample. We've got a Z average of 107.22, and we've got good repeatability between the results with a low standard deviation. So there are different things now that you can do once you've collected the data. If you realised that you hadn't quite got your analysis model right, you can go to reanalyze by right-clicking on the data set, and we could change the analysis model that we're looking at. With 100 nanometer PSL, you won't see a big variation between the analysis models because it's an incredibly monodispersed sample. So if we go to reanalyze there, you can see that it's populated at the bottom and it has the same size near enough. So if we go to the intensity distribution, we can confirm that. The other thing that you can do is if I shift and select all three repeats again, we can go to the Statistics and Overlay and then File, and we can export the data as a PDF. And then for ease, I'm just going to put it on the desktop and type in 100 nanometer PSL and save. So now if I go to the desktop, we've now got that file, that PDF. So you can see the software generates a really nice result that you could either use in your lab book. You could take the histograms for publications. Very versatile, whatever you need, you can do it. So you've got your Z average results across all three samples and your repeatability. So this is a simplified report format. If we go back into the software, and just select one of the reports, we can then go from the intensity distribution, for example, and export a result as PDF, and we can do run 1, for instance. And what you'll find is this is a much more detailed formatted report. So there are two types of reports that you can have by default in the software. Like I say, this is the detailed one where you get a lot of information if you're, for instance, going to plot the data elsewhere or use it in a different manner. And then if we go to Tools and Report Format and go to Standard and export the same data again, we'll name this one Standard. You can see it's a much more simplified version, but you still get the peak information breakdown. So in simplistic terms, that is running a sample on the BeNano 180 Zeta Pro. It's very straightforward, but you've got a lot of tools that you're able to use within the software to personalize how you want to use the system.